Welcome everyone at our weekly colloquium. Our speaker today is Professor Andreas Eckart from Cologne University. Professor Eckart also has been working for many years in the Max Planck Institute for Extraterrestrial Physics, of course in Germany. And he is also an expert in observational and theoretical astrophysics, leading expert in studies of central black hole in our galaxy and other low-activity galaxies. And today he will tell us about the Galactic Center on parsec and sub-parsec scales. Please.
Yes, thank you very much. Thank you very much for having me here and giving me the opportunity to summarize some of the more recent work. So what I will try to do is summarized in this little sheet here. I will put you through the most recent and most spectacular, in some cases, results, measurements on the Galactic Center. And I've subdivided it in a few points. They deal with the X-ray shadow on parsec scales of the CND. I will tell you exactly what it is. You will see some ALMA results on the Galactic Center. ALMA is a millimeter interferometer that is able to do sub-arc-second resolution imaging of that region. And then we will go to light, to the infrared light. We'll talk about the stars in the Galactic Center and how they orbit the supermassive black hole. And you will see that from that one can extract some information on relativity. One can prove that the environment is such that a heavy mass must be involved. There will be a very small intermezzo where I will talk about interferometry a little bit. Although it has been used before with ALMA, I will explain again in very brief sentences and mostly depictive how it is working, and then I will tell you what the difference is between radio interferometry and optical infrared interferometry. And then in the end we'll go to light and shadow, that is the X-ray and near-infrared emission and possible shadows that one expects, that all are a proof of a supermassive black hole in a way. And that will then close this little summary. So, a very short introduction at the beginning. We are talking about the Galactic Center that is located southwards. If one would try and look at the Galactic Center from here, from Europe, one would have a hard time. It would be very, very close to the horizon, as you can see up here. So therefore, we usually have to go to the southern hemisphere, and most of the time we go to Chile to do observations. And the Galactic Center is located at the center of the Milky Way, and with respect to the Earth, that is located approximately here. So the Sun is located at an inner edge of a spiral arm, and we have to look towards the center if we want to study the center. But that also means that we have to this is a Milky Way from the side, that we have to look through the entire disk. That is, all the gas and dust that is there in the disk hinders us from getting a clear view into that region. So that means in the optical observations are basically impossible. The extinction is 30 magnitudes. 1 magnitude is a factor of 2.5. And that means only observations in the radio, infrared, and X-ray domain are possible. So, I will briefly summarize what has been done so far. So, infrared imaging at high angular resolution has revealed that there is a central stellar cusp. The central stellar cluster is depicted here. So red stands for red and blue for blue. So blue are young stars, more or less. Red are dust-enshrouded stars. And one can also zoom into the very center here. And if one does that, one sees a number of maybe like 30 stars, which are at high velocity, and they're orbiting some point in the middle. And one of those stars here with this little ellipse associated to it, that is S2. And for S2, we have 1.5 orbits, or almost 2 orbits now. That means we can use Kepler's law to derive the mass and the compactness of that object. And it turns out to be a supermassive black hole, as we'll see in numbers in a second. That region here, if it is then a supermassive black hole, should also be active in some way. And that has been long sought for, but then finally found at the beginning of this century. And that was done with the Chandra X-ray satellite. And Chandra was able to detect flares from Sagittarius A star that is light excursions that went a factor of 10 or more above the quiescent state that the source has in the X-ray domain. And it also revealed some important information right with the first bright flare that was seen. You see here's a drop by almost 2/3 or more in flux density, and that happened over only 600 seconds or so, indicating that indeed the time scale shows that this must have happened very close to the supermassive black hole. So that flare emission was indicative for some accretion going on. Then in the infrared domain, that was also found a few years afterwards. In the infrared, the source was then detected and also showing flare emission. Here's a constant stellar flux level depicted in red. And this flare emission was detected from Sagittarius A star. And also here showing in the first instance some interesting feature, namely a quasi-periodicity, which at that point was heavily discussed and then later on a little bit disputed. But in the meantime, we know that there must be something real to it. I will show you the evidence for it. So all of that was very interesting, and it led to further investigations. And I will now go to the most recent details that we have found out about the Galactic Center on parsecs and sub-parsec scales. First of all, we go to the X-ray domain again with the Chandra satellite, and I will show you some images of that region. So this is a observation here in X-rays. Gray means flux, and white means no flux. And that has been done with Chandra with an exposure time of 4.6 megaseconds, and it shows you about 4 by 4 minutes, corresponding to about 9 by 9 parsecs of the center. So the Galactic Center is located here. So this is the deepest, most consistent image that was obtained so far. And looking at it and knowing the region, one sees immediately that there is some feature to be seen that had previously not been detected in the X-ray domain, namely a shadow of a different structure that was known from a different wavelength domain. As you can see here, it turns out to be a little bit brighter, here also a little bit brighter, and in this region as well with respect to the darkish background. And you can peel that out by modeling the emission to very coarsely with a Gaussian, subtracting image minus model, inverted, clip it at 0, and smooth the result. And what you then find is a structure like this. So this is the shadow inverted, the shadow of the central molecular ring, the CND, here shown in an ALMA image, and we'll see ALMA data recently in a while much better. So there's a circular structure, cloudy structure around the central stellar cusp, and that was now seen in X-rays in its shadow against the background. It's very nice because it is also consistent with the stellar distribution. Basically, what you see here is a 2-micron image of the stars, and with a dashed line I circumscribed the brightest region, and that dashed line is exactly the inner circumference of that shadow. So all of the darker regions here are most likely produced due to extinction from the CND that now is also seen in the X-ray domain. Now, with that information, one was able to subdivide the domain into different regions, like within the ring, on the ring, and outside of the ring. The data also allowed us to take spectra of all these regions, sum up all the photons, and this is a typical X-ray spectrum in the few keV domain that you can obtain with Chandra, and that then allows us to model the hot plasma emission of that region. And you can, what we did this with a 2-temperature model, so a lower and a hotter temperature, and you get information on the temperature and density. And so we could separate out the central region, the region of the ring, and the region outside of the ring, and could determine column densities and temperatures in terms of keV. And the result, if you interpret this, looks like this. The central region is the hotter region. There's a cool domain on the circumnuclear ring. And then again, you have some hot plasma outside. And it appears that the cool ring basically confines the hot plasma at the very center, and that very center also harbors a primary source for this heat, for this energy, namely the center stellar cluster. So this is the summary of that region. Basically, you have here another X-ray image, now energy coded of the region. We had seen a central ring here in a shadow, and we now turn a little later to the stellar content. Before that, we have a short look at the molecular content of that region in general. So ALMA's view of the cold gas. So ALMA is a millimeter interferometer that allows you to image sections of the sky with high angular resolution. I will explain in more detail how these interferometers work in a short while. And it's located in the high desert of the Atacama, and it consists of typically 40 to 50 telescopes, and they all can be combined and give a sub-arc-second beam characteristic with which you can then map certain regions. And that was done for the Galactic Center, and it revealed very nicely a structure that had been seen before in the radio domain, namely the so-called mini-spiral. So here again you have a point source at the center, that is Sagittarius A star. That is also quite visible in the radio and in the millimeter domain as a synchrotron source. And this plasma here that looks like the so-called mini-spiral is basically a mixture of synchrotron and free plasma emission. So various investigations could be done. We could also trace various molecules in this region, also then again to determine the temperature and the density. And we can also look at the dynamics of some of the regions. In particular, this is Sagittarius A star. This is the mini-spiral here in blue. In particular, this region here that contains this green-yellowish gas that had not been seen before in the millimeter domain. That's the so-called central zone. And it actually allows us to make a statement on gas actually falling still towards Sagittarius A star, because it had been seen before in the emission of hydrogen and in the emission of OH, that is a radical that also allows you to do higher angular resolution measurements in the radio domain at 18 centimeters. So with these molecules and structural information, we can make statements on the abundance and find that the abundance is slightly higher than normal, than local, than solar abundance. The excitation in that region is higher due to the strong flux, X-ray flux of the stars. And we have found, as I pointed out, this central entity that is most likely identifiable with a source that has been seen before, here also depicted in different frequency channels, and that indicates that a gas clump is falling towards the central region, and it had been seen here, these yellow contours in OH absorption, and now it is also seen in emission with ALMA. So that indicates the structure of the mini-spiral, that is gas dropping in, plus this blob of emission that we found also falling on top of the central region, that accretion onto this region is still ongoing. So that means the accretion leads to increased star formation at some stage, and also leads to increased accretion onto Sagittarius A star, then leading to activity, namely flux density outbursts. So this is a summary image now of everything I told you so far. We have the central stellar cluster. In the background, we have the shadow of the CND in the X-ray domain in gray. And we have from ALMA here very nice high angular resolution images of the mini-spiral, plus indications of this yellowish clump of material falling onto the central region. So now we can move closer in, because this was all on parsec scales. We would like to go very close to the supermassive black hole. First of all, we would like to see whether it is a supermassive black hole, which will not be easy and not very conclusive in a way. But we will use the light of stars now. And all of these measurements have been done with the VLT, that is the Very Large Telescope in Chile. That's the ESO arrangement of 8-meter telescopes that can operate by themselves and, as we will see, can be combined to an interferometer. And we'll look at observations of the innermost stars and see whether we can use them as a probe for relativity in that region. And this is a data sheet. So the observations have been done basically at 2 micrometer wavelengths. So there the extinction is only 3 magnitudes, so 3 times the factor 2.5. So that's much better than 30 magnitudes as in the visual. So there you can see stars individually and trace them in the Galactic Center. The region now is a little bit smaller. It's only like half a parsec or so. And, but we can zoom in with the high angle resolution that we have of 60 milli-arc seconds, corresponding to a very small fraction of a parsec in these infrared images. So we can trace individual stars. That has been done. And here I show the orbits of 3 of the innermost stars. And the star S2 here is depicted in blue. That is the one that gets closest of the bright stars that gets closest to Sagittarius A star. There are a few other, 1 or 2 other stars that also get very close. But they can be used here to probe the inner gravitational potential. So this is basically a map of the region, and this is the orbit derived from proper motions and from velocities. So velocities can be taken from the literature, and some of them we obtained by ourselves. So these are the velocity plots on these orbits for the different stars. And you can see that they go through rather excessively high velocities, reaching up to a few thousand kilometers per second during periaps when they're very close to the Galactic Center. Now this orbit needs to be treated, and we did this fully relativistically. We had done it previously using this ansatz here in Rubilar and Eckart, but now we did this complete ansatz here, and it basically allows you to, first of all, have a non-Newtonian extension, so you can treat to first order the relativistic effects. And in this equation, which is shorter, we assume that Sagittarius A star is fixed in space. And in this equation, we in addition allow Sagittarius A star to move as well. So this has all the degrees of freedom that are relevant. So basically, if you remove the curly bracket, yeah, this turns down to acceleration equals gm over r squared. That's a classical standard formula, but with these brackets, it can be used to treat relativity in its full extent. So that means we could fit the orbits relativistically, and that is needed if you want to make some statements on these effects. So some of the effects are listed here. So you expect transverse Doppler shifts. We will go to the spectroscopic domain in a second. Gravitational redshift that has been treated in those papers here. Peri-upshift, which we treated theoretically previously, but now we can make a statement on the measurement. And that has been published here in Parsa et al. Recently. And there's also higher order effects on which we still cannot say anything. We still need material or stars that are much closer to do so. That would be frame dragging or gravitational lensing. In a way, we have clumps that are very close. So we can make a statement on gravitational lensing, but not so much on frame dragging. So, looking at orbits very close to a heavy mass, one needs to take several things into account. There is a prograde relativistic orbital shift that you expect, but at the same time you have to be careful because you also expect to see maybe a retrograde Newtonian shift. because this object is flying through a distributed mass of stars. Yeah. It turns out that very close to Sagittarius A star, that is probably not a reason to worry, because the density of stars there is very low. But if you would be further out, you would see more material. In any case, there are stars, and if you want to keep on worrying about it, you also have to worry about the granularity of the distributed mass, because while the star is orbiting Sagittarius A star, there will be other stars underneath it. They will come and go. So the potential that the star sees changes while it is in orbit. So that may give rise to some higher order effects at some point. But so far, we don't see any traces of it. So what we have to do to detect the gravitational periapse shift is we have to detect a deviation from ellipticity. While in its rest frame it will stay in ellipse, in the observer's frame that looks at the motion, it will have a Rosetta shape. So we have to distinguish the Rosetta shape from the ellipse. And we did this in a very trivial way here, but very effectively. You can look at you can fit the orbit just using the lower half and the upper half, or the ascending or descending half, and then look at the different orbital elements, the long axis or the ellipticity of the lower and upper half, and look at their ratios. And those ratios are expected to follow a certain trend depending on the degree of deviation from the ellipticity. You can also look at the shift between the ascending and descending part. That would be delta omega, that would be the periapse shift. And that basically clocks through each time the source comes very close to Sagittarius A star. So if one would see traces of those things to change in a predicted and expected way, that would be an indication for a certain degree of relativity visible in the orbit of that star. So that has been tested out with test stars in the computer with relativistic orbits. And this is basically a parameterization of this delta omega against this relativistic parameter. So as a measure of relativity, with various things one can choose. We have chosen the Schwarzschild radius divided by the shortest periapse distance. And that basically measures the potential in a way. And as a function of this relativistic parameter, we measure these periapse shifts delta omega. And this is the formal fit to it. And that can be used to go in with the data and determine this y, this degree of relativity. And if one does so, then one finds that the delta omega that we observe is about 14 plus minus 3. And we expect for 4 million solar masses 11. And the degree of relativity defined as this quotient that I pointed out earlier is expected to be 0.00065, and we find 0.00088. So we have values that are in the range of the expected numbers that you would expect for a heavy mass like this. So we find a bit above 4 million solar masses and a distance of about 8 kiloparsecs to Sagittarius A star. Yes, that is basically a standard deviation obtained from a distribution of fits that we did. So depicting it in a little movie, you see the following effect. You see the stars orbiting. This is S2, and the periapse shift that we measured here indicates that the orbit has been shifted a little bit, so it's on a different orbit after one turnaround. So that's not the only thing that one can do. Well, this is trying to get a hand on the periapse shift. One can also look for the gravitational redshift expected from S2, from that star. And that has been done by the Gravity Consortium that we are part of. And before we go into this, because that used interferometry. I will very briefly point out some details how interferometry works, because it is very often not mentioned or forgotten. And I will do that here very briefly. So basically, an interferometric methods are a tool to construct yourself a bigger telescope. You are limited in the size of the telescopes that you can build to something like 10 to 100 meters. So you take two telescopes and place them at some distance. And you can think of them as being two sections of a larger aperture, right? And you can have many telescopes to have many sections of such a large aperture. And then you can combine them pairwise. And if you look at a certain source in the sky, you find this delay difference between the incoming wavefront. So that you have to correct for. You also, which is not depicted here, have to correct for the different velocities the telescopes may have with respect to the source. That is important if you have telescopes placed on different continents. But all of this has to be done. And then this interferometric method is basically an incarnation of the Zitter-Zernike theorem. So the Zitter-Zernike theorem, as you know, is a statement on spatial coherence. And it basically is a Fourier relation. And it relates the image of the source that you want to observe with the complex visibilities that you measure on the ground with the telescopes. And these two ways of writing the Fourier transform here are shown here. And as usual, the Fourier transform consists of the thing that you want to analyze. Here is the map, the image. And you basically fold it with a sampling function that samples all spatial frequencies. And that sampling function here is basically realized by the configuration of telescopes on the ground. So their separation indicates what spatial frequency, i.e. 1 over x, you measure. So an interferometer is basically a machine that measures complex image amplitudes, amplitude and phase. So the amplitude shows you how bright it is, and the phase tells you where the object is located in the sky and where the object components are located with respect to each other. Now you have a limited number of telescopes. That means in this UV space, that is the frequency, the spatial frequency domain. So U is 1 over x and V is 1 over y. Not all regions, that's not completely filled, as it would be filled with a single mirror. So you have these tracts. These tracts reflect the position of the source and the motion of the telescopes with respect to it. So if you have only a few telescopes, you're in bad shape. You have this little coverage. It becomes very difficult to make a map, an image, which otherwise you would just have to inverse transform. But you also have an arrangement like for ALMA, for instance, where you have a lot of telescopes, and this is a similar distribution here, but now it's almost filled, and that is a much better situation. So basically, you have your complex visibilities calibrated on top of these curves, and then you simply inverse transform that distribution into the image space, and you have an image of the source. However, you have an image of the source mixed in with the remembrance of the bad UV plane coverage, that is the dirty beam. So if you inverse transform, you have a mess like this, but due to deconvolution, because you know how the beam will look like, because that's a picture of the UV plane coverage, you can then deconvolve the image, and after some steps you have basically a artifact-free image of the source. So this is in very coarse points how you can do an image using an interferometer. But at the same time, it can also be used to do precise measurements of positions and motions, of course. So there's a difference between the radio domain, for which most of this is true and very simple, and the optical domain. So you both have the standard interferometer setup, but in the radio domain, you can correct, for instance, for the delay between the telescopes through a longer cable on this side. And therefore, you can basically shift the two signals to the same plane. You do have to do some other corrections then, and then you can measure the complex visibility. But in the optical, that is not possible. In the radio, it's possible because you can mix down your radio signal to an intermediate frequency where you can handle the photons basically much easier. But in the optical, you cannot efficiently loss-free mix down and stably mix down. So you have to stay in the sky frequency domain that is in the optical or in the infrared. And therefore, you have to do the correlation or the intermixing of the signals also in the infrared domain. And in addition, you have to correct for the delays also in the optical. That means the longer cable here, or the electronic delay, transforms into a moving mirror system, which is very painful because now you have to move the mirrors with a very high accuracy, because you want to sample light at distances shorter than the wavelength. So that makes it very complicated, and it means that you have to move mirrors. And here's a very, very short movie that shows you how at ESO these mirrors are moved in the delay line tunnels. So these are the tunnels in which these tracks go. And these tunnels go to the individual telescopes, and they combine the light and lead the light to the beam combiner lab down here. So this is where the interferometric cameras then are mounted. And this motion of that mirror can be done through various stages of correction at a very high precision, and precise enough to do the correlation in the optical. So that system, this VLTI, the very large telescope interferometer, has been used now for an interferometric camera that we have been building in a collaboration. So the collaboration's name is Gravity, that you probably heard of. And it is led by MPE, Frank Eisenhower in Garching, and various institutes in Europe participate in it. And at the First Physics Institute in Cologne, we built some of the core pieces of that instrument, namely the beam combination spectrometers. So the apparatus where the light is actually combined to form the fringes and therefore the interferometer signal. So that's the machine, one of the machines that we built. So many lenses, turning wheels, everything very precise. And at the end, you have a combining element, fiber segment, where the fibers realize the different combinations of telescopes into two telescope interferometers and some additional channels. Again, the beam combination canals here with people walking around that usually during operation would not walk around because they are a heat source. They would produce turbulence in the tunnel, and that would lead to bad measurements. So everything has to be very, very stable. Only the tracks will move very slowly to correct for the delays. And you see there are several delay lines because there are several telescopes and several two-telescope arrangements. They all have different delays towards the source, and they all need to be corrected individually. And this is the machine that we built, or in here are our spectrometers. This is a person working on this thing. And these are the first fringes that we measured. And from those fringes, it is then possible to extract information for imaging or for positional measurements, as discussed earlier. Now, that interferometer, that gravity, has been measured to provide a very high precision measurement of the orbit, while we had spectroscopy as well. And the spectroscopy now can be used to do the second test for relativity, namely the relativistic redshift measurement. So here is what it is. We have to go to the redshift as such, delta lambda over lambda. That can be expanded in these terms. And important here is the second term that carries the information on relativity. And that second term falls apart into two equally important terms, one of which is the gravitational redshift, and the other one is the relativistic transverse Doppler effect, as you can easily see here. So this is the angle to the line of sight, beta is v over c, and this here is the gravitational redshift. that is expected if the photon has to move away from a deep gravitational potential. So usually you cannot separate them. You measure all two of them at the same time. Yeah, but you can predict what they should be because you know the mass and the distances. And it turns out that this that the velocity that you measure, the velocity offset, will be of the order of 150 kilometers per second, which is easily measurable in principle because it only requires a spectral resolution of 10 to the minus 4 to allow you to measure that measurement. So a spectrometer has to be built to do that, and you have to have very exact information on the orbit. And then you can indeed do measurements of this effect and compare it to the prediction. And you see that in this case, we indeed measured approximately 200 kilometers per second, what we would have expected as a gravitational redshift effect for the star S2 while it is going through periapse. No, yes, these data have been corrected for the Newtonian part, and you are left with the offset you would expect due to relativity. Yes. Yes, yes. No, this is a precise measurement. Yes, yes. And the error on the mass is like a percent or 2% or so. So it's very, very precise. That was the reason why the interferometry was also used here. So here is the scenario. This is the orbit. This is Sagittarius A star. And this is the star moving by. You see everything happened in May. That's the pericenter. If you look at this, one question that is always asked, something must be wrong because the mass center is not sitting at the focus of the ellipse. That is due to the fact that the ellipse is inclined. Yeah. If you look at it from the side, the central mass point can basically be anywhere within the circumference of the orbit. So here you go with the mass estimate. So the mass is now 4.1 million solar masses, with a very small error, and the distance to the galactic center is 8,127 kiloparsecs plus or minus 31. So this is the precision that can be reached right now. But we can move even closer than that, and that's what we will do. So now we go again to light and shadow, and we will look at other systems that orbit Sagittarius A star. So far we have made use of the stars, but there's also most likely other objects that are close to Sagittarius A star that emit and that can be regarded as objects moving in an orbit around Sagittarius A star. So what we have done with S2 corresponds to a measurement of this relativity of about 1,500 Schwarzschild radii. But now we want to go to like 2 Schwarzschild radii or so, and that would mean this y of 1/2. So how can we do this? We have the X-ray view now, and this is actually something that we are doing with our colleagues, and Vladimir Karas is sitting in the audience in Prague. So together with the Prague people, we modified a code to be able to fit polarization data in the infrared domain. But we use this code also to predict light curves of emission of blobs. And that is the scenario. You have a blob orbiting a supermassive black hole on an orbit close to the last stable orbit. And while it is approaching, it is being boosted. And due to aberration, the light is enhanced. And if it recedes, due to aberration, the light is diminished and it fades away. And in addition to that, it runs around the backside of the supermassive black hole, depending on the inclination, and some lensing may be expected. So if you look on top of on the scenario with the different orbits, then this is the situation you have. The observer is here. You look at the supermassive black hole, and the spot is moving. So if it is exactly behind the supermassive black hole, you would expect it to be lensed. And then if it orbits around the corner, basically, it has components of motion towards you. In particular, since the light rays are bent around the corner, so you can look around the corner, you see it coming before it actually points towards you. And that means it is flying towards you, and due to aberration, the light is enhanced. Now this D is here positioned after the L, but actually the Doppler boosting starts a little bit earlier, yeah, and reaches a maximum around here and then diminishes. And that leads to characteristic light curves, yeah, that depending on inclination and distance look different, but they all have the same features. Namely, they have a shoulder here where the lensing occurs while the boosting already set in, and then comes the boosting peak here on top. So you expect a double horn profile, or at least a shoulder, if something is moving towards you on a relativistic orbit close to Sagittarius A star. Now, these are the 4 brightest flares at that time that we fitted, and they all show indications, stronger or weaker, for a shoulder that is indicative for lensing. You may say this is not very convincing, but here is another flare, the Ponti flare, one of the brightest flares that has been in the X-ray limit, has been measured so far. And here it very clearly shows at the same position, at the correct position, a lensing peak, and then followed by a boosting peak. So this indicates that material is orbiting with a high inclination and gives rise to modulation of these X-ray flares. And actually, the method can be used, interestingly enough, to determine the mass of the supermassive black hole. Because what we have done, and this is shown here, the period in gravitational units, and this is the period in units of time. And here you see the usual terms. What we have done is we have taken the light curves in periods, so scale-free, and fitted the flares. And then one can reintroduce the scale by telling the routine how long the flare actually is in seconds. And if you introduce the time scale, you automatically get, basically for free, the mass. And that is depicted here in this formula. Yeah, here you have the observed time scale in seconds divided by the time scale in gravitational units, and out you get the mass. So we did this for all possible inclinations and distances, and looked for a median answer of this, and we could do this with 4 different flares, and we obtained of the order of 3 to 4 million solar masses, as we would have expected. So we also get from this fitting the correct answer, this time determined from X-ray flares for the mass of Sagittarius A star. And in addition, we also were able to apply this to an extraterrestrial supermassive black hole to check it. Now, we have been very close looking at orbiting blobs, presumably in the X-ray, and what flare emission they produce. We can get even closer and have a true look on how these spots move by using near-infrared interferometry. And this is again a paper from the gravity collaboration. And here again, the paper and the many authors and the machine that we built. And this is the data. What is shown here, what gravity can do is it can image, but the imaging would only be at a resolution of about a milliarc second or so, or 2. But as an interferometer, it can measure the position very precisely, and it can do that with a precision of the order of 10 microarc seconds. And 10 microarc seconds is exactly the precision you would need to see the spots moving around the supermassive black hole. And these are the measurements of one of the brightest flares that was observed. So these are the measurements consecutively shown by the arrows. So they show an almost filled motion of the center of gravity of the image moving around. So the source moved around in the sky like this. So the most of the light was coming from a blob that apparently is in orbit about something, and that something is located approximately here, and is identical with the position of Sagittarius A star. So that's the same information here in X and Y. That's an image, really, that shows the motion. And this is the flare emission. That's the light curve while these measurements were taken. So that's, again, the image. And this is now the image on top of simulations that, again, have been done also by the colleagues in Prague. So that shows you how a continuous ring of emission would look like at a certain inclination, and you can place basically those spots on top of it, and this is what you would expect, and this is what we actually measured for not only one flare but for a total of 3 flares.
Excuse me, but if you imagine that you have a jet and if you have a kind of helical structure in the jet, perhaps the image will look still the same.
That is true. At that point, you cannot exclude a short jet. Yeah, that means that the source that we see here would sit on top of a disk-like structure and would rotate, would show orbital rotation as well. But it is not a pure jet component because that you would expect to move away. Yeah, so that can be excluded. It is orbital motion that we see here. It's not linear motion as you would expect it for a jet, most likely. So one can also do a little bit more physics with it. You can look for different scenarii for prograde, opposed rotation, and no rotation at the expected positions here, distance and period. And these are the 3 flares that were observed, and they are all in agreement with a mass of 4 million solar masses within the uncertainties here, about which this orbit was in motion. And this is in addition also supported by polarization information that was obtained at the same time. So that's the situation in total that we have now from the infrared. We have the stellar cluster with different stars. We have the high velocity stars in the vicinity of Sagittarius A star, the supermassive black hole. They can be used to exactly determine the mass and the distance. And they also can be used to get a first glimpse at the periastron shift. That will be possible with a much higher precision with the interferometer, but some more data has to be taken to do this. And due to the interferometer, we also now see for the first time spots moving about something, namely, and that something is at the right position and has the right mass of Sagittarius A star. So now one now may ask, what is the radio interferometry doing? Because you may have heard that the Event Horizon Telescope is out on a big campaign, and there will be a press note on a different source coming out very soon, also observing Sagittarius A star. No data has been released yet. Data has been taken, and no information is known really of what the thing looks like. But there's other radio data of similar arrangements, like the Event Horizon Telescope, that have been published. And here's a paper by Ruzen Lu et al. And they have obtained radio interferometry measurements. Here's the UV plane coverage, which you know by now, of Sag A star. And they model their data. They don't image it because the UV plane coverage is not good enough, but you can model the data. They model the data as either something that is orbiting something else, that would be orbit of a hotspot, or something that is distributed and brighter on one side, which is basically the same. Yeah. So it is indicated that one may see a very similar structure in the radio domain. But we have to see what the radio people actually come up with. And yeah, and you can now also put this all together in a much bigger framework, namely what can we say about relativity as such connected with masses. And this is the famous Psaltis plot. What you see plotted here is the mass of the object in gram, logarithmically, against the measure of the potential. Yeah. So the black hole would be up here, the event horizon would be here at 0, and these are basically distances to the black hole event horizon. So this is what you can achieve in terrestrial labs. If you do pendulum experiments or other experiments, this is the precision of Mercury. That's also a measure of the relativity, basically. This is the Shapiro effect. That's the Hals-Taylor pulsar. This is now the delta omega measurement that we came up with by Parsa et al. And this is also the gravity result, measuring the orbit of Sagittarius A star and the intergravitational redshift. This is where you would be with the X-ray hotspots by Carson et al. And the gravitational hotspots that have been measured now with the interferometer that I showed to you. And this is here what you would expect, what you have from gravitational binaries that have been observed using gravitational waves. So we are padding out the domain from laboratories all the way down to Schwarzschild radii for different masses, right? So here we go to super massive black holes. This is Sagittarius A star here.
I would add here quasars as well, because radio-quiet quasars emit most of the radiation at distances like 10 Schwarzschild radii. This is what ideal normally is, true. And they see there as well.
That is true, but in many occasions these statements have to be made indirectly by adding some other pieces of information. All these measurements are relatively poor, and they are true measurements of indicators of relativity. Quasars, they fall also in this domain here, same mass, also very close to the black hole event horizon. But the quasar phenomenon is rather messy, right? You have lots of flux and lots of accretion taking place. But you're right, they would fall into this domain here as well. So that is a summary of the topics that I presented. So we have gone from large regions, parsec regions, have seen in what environment the supermassive massive black hole is located in, namely in the central stellar cluster, that by itself is located in a hot plasma that can be seen with Chandra. And then we have looked at various indicators, namely stellar motions and motions of spots orbiting Sagittarius A star that indicate a certain and expected degree of relativity that you would find for 4 million solar masses close to the event horizon. And we may conclude with music and this journey into the center of the Milky Way. And that is something you can download from the ESO website that has been done by the Gravity Collaboration and ESO, and depicts very nicely the journey now. We move towards the center. Dark clouds occult the optical light. We have to switch the wavelength domain, which is being done now, to 2 microns. Now we see the central stellar cluster, and we see the central bright stars. This Iris 7 is a supergiant that helps imaging a lot. These are the hot stars, the helium stars. This is the small high-velocity stellar cluster close to Sagittarius A star. We now go to stellar motion measurements. This is a concatenation of measurements. You can see S2 orbiting, and you see flickering where Sagittarius A star is located with flares. And now we get a fine, detailed measurement, as it is done with the interferometer, of the orbit. That happened in May last year. So these are the locations of the measurements. And then we can move in, and we have seen indications for spots orbiting very close to the event horizon about Sagittarius A star. And all this bluish stuff here is sort of artwork. So thank you very much. That was the journey.
Any questions?
Thank you very much. That was working. That was actually very nice, also introduction to someone from less familiar with the topic. I myself are a cosmologist, also working with the different theories of gravity, so this is already announcing my question. You gave a couple of quite precise numbers, especially in astrophysics. They look precise with the small errors, and that's why it's very impressive, especially gravitational redshift measurement. I would be very interested in your opinion as an expert. How much of the freedom is there in respect to the post-Newtonian testing of the different scenarios than GR itself? So, in other words, how much of the GR you assumed in data modeling, or there are measurements that you don't assume GR that much, so you can really test the GR, saying that this has been tested and there's no room for other theories. And if there will be more time later, I might have this other question.
But I can answer it. First of all, the high precision that you indicate, the high precision is really high precision, and it comes about because all geometrical details of the interferometer are measured out to a micrometer scale, basically. And we can trace the photons on micrometer scale. So we have exact information on this topic. And if you take that ground position, and put it in the sky, you get these numbers, right? And the measurements are only possible with that accuracy. And then, yes, we have done these measurements, and we have compared them with sort of first-order post-Newtonian expansions, this simple relativity. You can certainly use other forms of relativity and apply them to that, and that is actually a problem, but maybe in the near future that can be solved. What you have to do is you have to go to even higher precision, and see whether you can trace these effects. That may be very difficult. For instance, one thing that was pointed out that might be indicative is the shadow of the black hole. But it is actually shown, it can be shown that the shadow of the black hole can not only be explained by relativity, by standard relativity, but you would get similar shadows, for instance, from other objects like boson stars. So if you, now I'm not talking about different relativities, but I'll talk about completely different objects. What can be excluded is neutrino stars, because for a standard neutrino mass to describe all supermassive black holes in the universe with one particle and not design a particle for each supermassive black hole, Sagittarius A star would be too large, and that would result in Newtonian periastron shifts, which we would clearly see. So that can be excluded. But boson stars are very, very compact, although they are based on a speculative repulsive force that is not existent. No other measurements are done for that, but nevertheless people talk about it. But they're so compact that you would get similar results. However, a boson star is a very fragile object. If you kick it, if you accrete on top of it, it will collapse and form a supermassive black hole. And you cannot rotate. So, and we know that accretion is taking place, or at least we see flux density variations. So we see that something violent is going on. So if it had been a boson star, it would have collapsed to a supermassive black hole, most likely. But the really interesting point is now that apparently the measurement tools are in place to do precise measurements to allow now for these investigations. That's
why I said I was really impressed.
Yes.
Okay, more questions?
What would be the road ahead? I mean, if you could move your, do you expect anything new from Webb telescope, or if you could move your instrument to the moon or elsewhere outside of the atmosphere, how much would you gain?
Well, from James Webb, concerning these observations, we won't expect anything. James Webb is at a much longer wavelength, 10 to 50 microns, and it has an angular resolution, although it's an 8-meter class telescope, that is of the order of a fraction of an arc second. Here we talk about 10 micro arc seconds. What James Webb will be good for is investigate the 10 micron region spectroscopically and also in terms of flux densities. And one thing is still missing. Sagittarius star has not yet been detected in flare emission in the 10 micron domain. and that may be important to make further statements on the emission mechanism. Yeah, so that is something interesting I'm looking ahead for. In terms of phase space for the interferometer, of course, one thing is to get more flares measured. Yeah. Right now, the indication, I didn't mention it, is that this orbiting spot that was measured was most likely on an inclination that is rather 45 degrees or a little bit flatter, so rather face on. Whereas the X-ray flares that I showed are indicative for higher inclination. So that does not exclude itself per se, because it is not necessary that a given plane is there along which the accretion goes. There may be stuff coming in under different position angles and inclinations, but that needs to be certified statistically. So the task would be for the near future to do these measurements while S2 is moving away, because S2 was very helpful. It could be used as a phase referencing source to measure Sagittarius. It was in the same fiber, but now it moves out of the fiber, and we have to do the true thing for which gravity was designed, namely a dual channel interferometer. So we can fringe track on one source and measure science measurements on another source. We know the differential delay and we can correct for it. But that has to be put in place now for the new measurements.
Okay, anyone else? Agnieszka.
I want to ask about these flares actually. So how often do they occur, or is there any periodicity suspected to be behind them, or it's just a random event, such flare?
Yes and no to all points. They occur very often, like the very bright X-ray flares, like 10 times brighter than the quiescent emission, occur once per day, approximately. And then standard flares occur. Standard flares occur in the infrared occur like 4 to 6 times per day. So basically, each time you go to the telescope, you will witness a flare. So that makes it very convenient to investigate them. Then the distribution of flare fluxes follows a very strict power law. So they appear to be random, but have a power law, and the power law is limited. So there's no power for flares longer than like 150 minutes or so. In other words, you don't go to the telescope and see one night Sagittarius A star off, and the other nights you see it on for the entire night. Yeah, that doesn't happen. So they all last like 20 minutes to 4 hours or something like that. So that can be said for on the power law. And yes, one expected quasi-periodicity from the first flare measurements that I've shown, because that has this wavy structure. Then the detailed statistical analysis showed that it's more a power law, yeah? Although it has a peak power in the half-night domain. Yeah, so very likely something quasi-periodic on that time scale will occur, but it doesn't stand out as a signal, yeah, because it's only quasi. It's not periodic, it's a very quasi. Yeah, and now, but this, so that was then refuted, but now this idea pops up again because we do see matter orbiting. Yeah, and from orbiting matter, you expect quasi-periodicity. So that is the no answer to this question. We do not yet have the full picture. So we still need to have a model that both includes orbital motion and the statistical characteristics of the source to fully explain what is going on.
Okay, anyone else?
So I have time for my second question. So you said that the earlier the ansatz first you used, you had the fixed black hole position, and then you make recently a move toward releasing this degrees of freedom. But actually, how much constraint of the observational we have of the peculiar motion of the well, I know it's not directly observable, but I guess that there must be some limits.
Yes.
And how it was important. I would be really interested.
Yes. There are limits. I cannot give you the exact number now, but we are within these limits still. And the limits come from radio interferometry, because if you look at Sagittarius A star as a point source and compare its position with respect to nearby quasars, then you see the reflex motion of the sun orbiting the galactic center. So with respect to the stellar background or quasar background, Sagittarius A star moves, just like the Earth moves around, right? And that motion can be traced and fitted, and from that come limits of proper motions in certain directions. No, I don't know them. I don't know about them, but you can easily find them. It's in the literature.
Okay.
So maybe what you didn't mention, so you also mentioned lensing as one of the possible tests, but this is probably quite problematic observationally, because these lens images are faint also in infrared in comparison with stars. But maybe you haven't mentioned gravitational waves from Galactic Center. So what are the potential prospects for that? Probably not at higher frequencies, but at lower frequencies like millihertz or below. So
yes, of course. I mean, if you have an event that produces gravitational waves, like a heavy mass, an intermediate mass black hole that has not yet been proven to exist in that region, or at all, at least, if that would fall in, that would produce gravitational waves. Yeah. And you would be close enough and sensitive enough to measure those in great detail. The problem is the likelihood that that happens is very low. Typically, a stellar collision or something that is being torn apart by differential gravitational forces is of the order of 10 to the 4 years. One object per 10 to the 4 years, typically. So that it's unlikely that we will observe that. Whereas the gravitational interferometry people, they are very happy with these numbers, because they look at the entire local universe, and that extends out to the Virgo cluster and even further, the local bubble, basically. And then you have a large number of galaxies. Yeah, and if you multiply that with the low probability, then you get numbers of something like one or a few per day. So they expect these things to happen, to measure. But for Sagittarius A star itself, it's very unlikely that you will find such an event. But it will, of course, it would be great. Yeah. Also, what people are looking for, as you know, is pulsars, right, in the immediate vicinity of Sagittarius A star. That's also very unlikely to find it. But one cannot fully exclude it that one would find one. Yes. So because the number density of pulsars, although it goes up towards the center, the volume in which you search goes down by the cube, and so you're left with nothing once you arrive at the center.
Okay, so I suggest we continue discussions with coffee and cookies upstairs. Let's thank Professor Eckart once again.